This conference will now be recorded.
Alrighty, I think we're on. So, well, thank you again, Fran and USGS CDI for inviting us over here to give this overview on really an experiment that Bill Teng, Arif, and myself are doing together with members of the ESIP Agriculture and Climate Cluster. So Bill Teng, who is also on the line, he and I are co-leads for the ESIP Ag and Climate Cluster. And Arif, so both Bill and Arif are at NASA Goddard. I am an independent consultant. And together we started this experiment about 2.5 months ago, right in the middle of February, I would say. So as of now, this experiment it is still an experiment, and we are still at the very early phases of this experiment, although we're moving pretty fast. So I wanted to give you some qualifications for what you're about to see, being that this is mostly experimental and evolving fast. So the stuff that I'm going to show you is not, unfortunately, not totally logically consistent in many places, but what we hope to see is that you will come away from this presentation getting a good overview of what we are trying to enable, and the keyword here is trying to enable, meaning that you will see that what we're trying to do here is pretty ambitious. You know, we are under no illusions that we will be able to do this ourselves, nor in any short time frame like 2 or 3 years. I think this is a much longer time frame initiative, and we are really looking for help and looking for contributions, which may or may not be coordinated with us. I mean, feel free to spin off on your own if you feel that this presentation has given you some ideas. But with that, let me launch into the presentation, and we will try to finish this right around in about 25 minutes time. So the challenge that we face here is almost all of you actually are involved and or have been very much in the know about challenges arising from global environmental change, and with the attendant issues of adaptation and hazard mitigation. And the way that we need to think about adaptation and mitigation is that it is a continuous process from now here onwards. And I say this because, for example, when this was more than 10 years ago, when we were in discussions with the US Global Change Research Program, the USGCRP, there were a couple of meetings where it wasn't necessarily the USGCRP folks, but folks around the table who have been invited to workshops with the USGCRP folks had talked about adaptation as if you were one shot effort, like we need to adapt for the future. But I think the growing realization over the past decade is that we are in this for the long term. That adaptation and hazard mitigation is with us to stay for the next couple of 100 years until we get some stabilization of the impacts of climate change. It's going to be here. And so one of the things that we tend to think about is how do you inform these adaptation and mitigation processes with the best available science, with the best available data. And since, again, we're here for the long run in terms of adapting to these growing hazards, you would ideally like to have science-informed, data-driven solutions that are traceable, technically defensible. When I say technically defensible, it means that you have to be able to defend the choice of your actions and the selection of, for example, what your expectations of, for example, sea level rise are. What is your expectation of the anticipated precipitation rate per hour for this given period in time. All these that will lead you to a decision that you need to implement needs to be technically defensible, and you need to be able to reproduce it. And in some ways, this harks to the discussions about open science and reproducible science. It has many parallels, not totally identical, but has many parallels. Your solutions ideally should be repeatable and repurposable, and especially repurposable. You will see towards the end of the presentation why the concept of repurposable comes in. It sings a pretty strong hymn in our thinking. The repurposable means that the solutions need to be recombinable in the very same way that, if you are geneticists, you have DNA libraries, and you are able to actually assemble unique genomes, right, from combining parts of genomes from different organisms into a target organism's genome. And so you will see that being talked about later in terms of the resilience genome, in which we are envisioning that, if you had fully technically traceable, if you had fully traceable resilience plans that would trace the data and models, you could conceivably, with the help of a machine, discover plans out there which somebody has already written for a climate adaptation challenge or a hazard mitigation exercise, that where you could swap out parts of those plans. You could swap out, for example, relevant the data which is for one location, but you swap it in for another location which is relevant to your study, that kind of thing. And so, which is why visions of genome engineering and genetic engineering creep into our lingo, as you will see later on in this presentation. Now, so the way to think about traceability, of course, this diagram that is presented here, you would start on the left and work your way counterclockwise. But traceability, you can think of it as starting from data, where you have data repositories and various data sources in situ and remotely sensed, right, being used, ingested into models and collaboratories to generate indicators, right, that are, and indicators together with other data products, of course, are eventually ingested into publications and assessments that inform societal benefit areas like risk management, resource management, and so on and so forth. All right, so this flow around the diagram, you might see this in the various snippets of documents that this little project has spun off. You will see the term D2D, data to decisions, and this is what we mean. But also with the emerging cadre of early career scientists, for folks who have like recently graduated with the PhDs or the masters, there has been quite a bit of interest, not just recently, but I guess for the past decade and a half, of coming to say Washington DC, where I'm based in, and signing on for like a AAA Science and Technology Policy Fellowship, where these graduates are placed into agencies to help figure out places where science can inform decisions and policy. So this diagram also speaks to that, and you will see that what we are trying to do in terms of the concept maps also speaks to trying to connect science to policy. So keep these in mind as we actually go along. Now, before I actually show you the conceptual underpinnings of what we are trying to do, I think it is useful to situate us in an actual example of what the concept maps look like, so that when I give you the abstract view of what the concept maps are supposed to do, you have an idea of what the concept maps actually look like. So what I'll do here right now is to show you a couple of concept maps that have been created as an exemplar of what we're trying to do. So this drive-by, we're gonna suspend this presentation for a bit. We're gonna go to look at the concept maps, but this drive-by is based on the 2012 Hyde Park fire west of Fort Collins, which for I used to, by the way, I used to visit the Federal Center in Denver, the USGS Federal Center, and so some of you folks actually might identify from there. So this, just to let you know that the High Park fire is one of the fires that we're using to design our use cases around. We actually have in mind 6 use cases, all clustered between Denver to Fort Collins, right? West of Denver, west of Boulder, west of Fort Collins. So the High Park fire is one of those fires that we are using to build our use cases around. The major elements of these concept maps that you are about to see, all right, they address mitigation. So under the National Preparedness Framework, yeah, so this is stuff that goes back to the Obama administration. But if you look at the preparedness concept, you have preparedness through mitigative activities. So that is the first example that we will go through, mitigation. But later in the talk, we will also show you an example based on response and emergency response. This was just finished last night, so it's still rough at the edge. But the response, emergency response use case is based on the High Park fire. Now, and we will come back to the rest of this areas that I listed here, the national and interagency programs that the use cases address. So for the first use case, which I will not spend too much time on, we will only talk about mitigation. We will leave the rest of this stuff, the BAER, the BARC, and land fire. We will leave all this to the second half of the concept map drive through. So I'm going to momentarily pause this presentation and go over to this concept map. Now, so this, for those of you who have played around with concept maps a bit, the tool that we're using is CMap, concept map tool for the desktop, and there's an equivalent online version. The qualifier here is that CMap tools is not quite scalable if we are trying to really do what we're trying to do. So we do not foresee using CMap indefinitely. At some point in time, there needs to be a different tool. But for now, this tool and this screen that you see here is generated by CMap. And we're going to go through, again, the Colorado wildfire use cases. And this, what you see here is loosely, yeah, you could call it a concept map, but I would prefer to call it a narrative concept map. And you will see why the term narrative is important in a few seconds. For one, you see that we start the narrative off with this wildfire mitigation narrative, right? Starts with the 2012 wildfire season in Colorado, right? Which led to then Governor Hickenlooper forming a task force. Now, the way that I have structured the narrative so far, things like starts with, which led to Governor Hickenlooper forming a task force. For those of you who are thinking like, wait a minute, this is going to be hard for an algorithm to make sense of what this is, and you are right, which is why this is a narrative concept map. There are concept maps underlying this narrative. So this narrative is meant for human consumption, not for machine parsing. But the underlying concept maps that form the basis for this whole narrative, now those concept maps are ultimately, right, not right now, but ultimately, we hope, meant for machine ingest, so that the machine can do some inferencing based on the concept map. So again, the part where I said, the machine, we want the machine to do some inferencing with the concept maps. Now that belongs to kind of the vision for what we're trying to do. It is not easy to achieve that, but that's the vision, and that's where if you have expertise in ontologies or in deep learning or natural language processing, that's where you could say I know how to solve that bit of a problem that you guys have, and let me run off with my ideas, and that's fine with us. Okay, but to continue the narrative, so remember, this is a human readable narrative. So we talked about the 2012 wildfire season, we can take a look at the concept map that gives you a little bit more details about the wildfire season, or the wildfires in Colorado. And so here we have a draft concept map that starts with major wildfires in Colorado, all right, organized by the 2012 fire season, the 2013 fire season, the 2010 fire season, all right. And so this fire, for example, the 4 Mile Canyon fire that happened in 2010 west of Boulder. This is the one that we'll be focused on, High Park Fire. The Waldo Canyon Fire was something that we were looking at also initially. I think that happened down in Colorado Springs. But this concept map here gives you an idea of a map which we hope that eventually will be ingested by a machine and somewhat interpretable. So if you look at, for those who deal with ontology, so this relation has part here and has part here, that is actually taken from the basic formal ontology, or BFO. So some of these relations are actually formal ontology terms. I believe it's cited by, I don't quite remember, it's cited by, maybe also be a formal ontology term. But things like can be categorized by, no, that is not a formal ontology term. So if the machine attempts to parse this concept map, it will choke at various points. So that is a well-known limitation right now of the approach that we're taking. But we feel that there is a way to get around these. We feel that there's a way to get around these points where the machine will choke up because it doesn't understand what can be categorized by means. Anyway, just to close this window and return to the main narrative. Now, I had mentioned also that one of the things that we wanted to do was to trace how decisions ultimately trace back to data. So this narrative is not complete, but if you follow this path where my cursor is hovering, the path will end up in Landsat data. And let me just quickly go through that path. So when Hickenlooper formed the task force, all right, the task force issued a report that recommended using this thing called the Colorado Wildfire Risk Assessment Web Portal, CORAP. They advised that CORAP can be used by communities, right, to develop community wildfire protection plans, CWPPs. And actually, if you do the trace, we wouldn't go into that here. CWPPs are actually mentioned as an important aspect of healthy forests in the Healthy Forest Restoration Act of 2003. So actually, this thing called CWPPs, it's a national program, and it is linked to statutory requirements. But coming back to CORAP, now you will see that if you do the trace, and this involves a bit of literature search and going to various websites, but CORAP, which is maintained by the Colorado State Forest Service, the CSFS, CORAP actually ingests the interagency land fire data. And if you again trace back from land fire data of the specific data sets that are ingested by CORAP, they actually trace back to Landsat data. So this traceability has not been completed in detail, but ultimately what you want to do, of course, is to be very specific that Landsat, there's so many data products from Landsat, and you want to really know which are the specific data products that traces way up to land fire. And the land fire interagency group, those guys will apply their own algorithms to Landsat data. So what are the algorithms that they apply to produce their data products, the land fire data products that are ingested by CORAP? So at some point in time, it is ideal to be able to capture that traceability and document it in the concept map in some manner or other. And the reason, of course, is so that you want that traceability information to be available to a query mechanism where somebody could ask to see what are the useful data products that can be used to inform a community wildfire protection plan, the CWPP. Remember, the CWPP is a national program. So it would be useful, for example, for a pretty smart search capability to say that, to automatically detect that, you know, you are situated in the state of New York, and we have a CWPP that shares some characteristics of your climate, but it does have certain unique characteristics which does not quite meld with a New York climate. But you know, you might be interested in this CWPP anyway because you could modify it. And so it is things like these kinds of search capabilities that the NASA Goddard folks like a riff on the phone are thinking about and are experimenting with. Okay, so this is the one example that I have given about mitigation. So let's go back to the presentation and go on to the next part of the talk. So now that you have an idea of the narrative and the concept maps, what a concept map looks like, you know, the concept map meaning, again, the concept map is represented here in this diagram. It's a complicated diagram, but we shall explore it part by part. Oops, a little bit, yep. So the concept maps in the repository, we are seeking to develop a set of concept maps that mirror the data to decisions pipeline, the D2D pipeline that starts with data ingested into code that ultimately is ingested into information which informs decisions. So the concept map that you saw about wildfires in Colorado, that belongs more to this end, not quite decisions, but it belongs to kind of the fuzzy knowledge kind of things. If you were to talk about Landsat data, this would belong to here at this end of the things. And later in the talk, I will show you a concept map related to a specific Landsat data product that is more on this end of things. Now, the user narrative is what you just saw, you know, the human readable narrative meant for human consumption. Now, that user narrative is generated from specific nodes in the concept map repository. So I picked and choose concept maps, right, that you could drill into, but will represent it as a narrative. Of course, in the narrative, you could foresee that you might write a narrative in the form of just a Word document with hyperlinks to the underlying concept maps, and that's totally fine too. There are multiple ways of doing this, but in our vision for 3, 5, 7 years into the future, going back to what I mentioned about resilience genome and having a machine help you slap together a resilience plan for New York State, you know, having the machine actually know some of the things that you're trying to look for. Now, this is the part where we have to look quite a bit into the future and imagine that there is an algorithm out there that somebody would develop, which is capable of ingesting the concept maps in the repository and creating, for example, this reflects A1 to A2, A4, C1, C2, C3. This represents, for example, a series of planning steps in a climate resilience plan. So imagine this is a climate resilience plan that the genome extractor, which is an algorithm, picks out from the concept map. Again, not quite as sci-fi as it sounds. Actually, we kind of know roughly how to do it. But continuing from there, these genomes, right? One of these genomes is plopped into a genome library together with other genomes. So there might be a resilience plan from New Mexico State, and there might be a resilience plan from Colorado, from Durango, for example, a resilience plan by Boulder, and so on and so forth. Now, what you see here on the screen is the vision where the human user submits a human readable text. For example, the text here that I've give you is actual text retrieved from something called a BAER, which we will come across later. It's called a Burn Area Emergency Response. So in the case of the High Park fire, within some 10 days when the High Park fire or any fire is contained, if the fire is on Forest Service lands, within 10 days, the team, there's a BAER team, the burn team, in short, has to submit a request to the Forest Service and other agencies to request monies to stabilize, for example, the slopes. Because once you have burned slopes, as happened in 2012 and 2013 around the border area, once you have burned slopes and there's heavy precipitation, you may see debris flow and flooding events, and we know that to be true. So within 10 days of containment, the Forest Service folks, in this case, needs to submit to headquarters a written narrative. And the idea that we have in mind is for the Forest Service guys to submit the human readable narrative to the machine. Machine will pick out a relevant plan, in this case, a response plan, an emergency stabilization plan from the genome library, and present a bunch of candidate plans to the user so that the user, the emergency responders, can select and combine different parts of different plans from previous emergencies and use it to inform their plans. Now, so the important thing here to note is that we want ideally plans which are traceable back to data and models, right? So that is the vision. So it's pretty ambitious, but that's what we are hoping to enable, right? So let's quickly, I'm gonna just quickly go through the rest of the presentation. I'm gonna show you the emergency response and how the folks in Colorado have done it in the past with regards to the High Park fire. But just to reinforce that these concept maps are meant to serve multiple purposes. You know, self-paced education. If you're interested in finding out more about wildfires and how things are managed in a wildfire scenario, this is one way to dive into concept maps to figure out how the Forest Service does it, or how the USGS does it also, right? Is for transdisciplinary engagement. Knowledge discovery, this is the example that I talked about earlier, where you want the machine to do a context-aware search based on some search criteria. The search criteria could be a bunch of query items that you fill in the form, as we have all done, or it could be you submitting a one-page human readable document for the machine to try to figure out what you're after, right? And the most ambitious, so this part, the knowledge discovery, we think is somewhat, it is very doable given current technologies and methods. This part is very hard. This is the resilience genome part, where the machine helps you to piece together a resilience plan or mitigation plan that is traceable to data and models. This part is hard, but again, this is what we're trying to enable. Now, for the last part of the presentation, let me just very quickly show you the other narrative that corresponds to the High Park fire: emergency stabilization burn area response. Again, this will trace back to Landsat data. In fact, I will stop right here and show you instead of explaining. So this is the High Park fire narrative. Okay, the first part of the narrative is very similar to what you saw previously for mitigation, right? This wildfire, oops, actually it should be a response anyway. This wildfire narrative starts with the 2012 fire season, but the 2012 fire season includes the High Park fire, right, which ultimately led to major flooding in Larimer County, so places in Boulder and thereabouts. Now, if you look at how the authorities responded to the High Park fire, they documented, once the fire was contained, they documented their stabilization needs to, whether they need to build additional water channels to divert water that might be coming down from, that might be running down the slope in the case of a precipitation event. So they documented their emergency stabilization plan in something called a BAER, the Burn Area Emergency Response Plan, right? The BAER includes a section titled Burn Severity that estimates the area of unburned, lightly burned, moderately burned, and intensely burned land. If you look at how this data was derived, they use data that is ultimately traceable to Landsat reflectance data products, including, let's start with this one, including the Landsat difference normalized burn ratio, the DNBR. So this is one of the underlying concept maps that is ultimately supposed to be machine readable, I'm sorry. So if you look at the Landsat DNBR, how it's calculated, right? This concept map gives you an overview of like this DNBR is calculated from the normalized burn ratio, the NBR pre-fire minus the NBR post-fire. And both these NBR numbers, the Landsat surface reflectance normalized burn ratio, I'm sorry, it's a mouthful, but the NBR numbers are in turn, the pre and post-fire NBR numbers are in turn derived as such. So it shows you the derivation formula for the normalized NBR, normalized burn ratio, I mean, and some other information about which bands of the Landsat, depending on which Landsat instrument on which Landsat platform, gives you some information about how the NBR is calculated. So again, this is a lower level concept map, which we hope to be ultimately machine readable. All right, so let me try to finish off the presentation, and by perhaps just diving into the known problems, and we don't have time. Maybe we can talk about these amelioration challenges, about how you ameliorate these challenges later in the time that we have left. But yeah, the issue of scalability of this approach is a big concern, because there's going to be a limit as to how many and how complex your concept maps can be. Again, there are ways around it. We don't have time to get into those in this discussion. It is labor intensive. There's no way of getting around it. These concept maps are useful, I think, on a very personal level, because it helps whoever's writing the concept maps get a very much better understanding of the area of concern of the topic, but it is quite labor intensive. The amelioration mechanisms, I will not go through these in detail. I'll just leave them there for you to take a glance at them. I will talk about our next phase that we hope to experiment with, which is the last bullet point, using label property graphs. So Neo4j, for example, I've been looking at Neo4j for actually the past 2 years or so, on and off. So one of the things that we are probably going to experiment with in the next few weeks is to ingest some of the concept maps in CMap into Neo4j. And you know how the concept maps in CMaps are disconnected, but they have links to each other, of course. So we hope to almost like denormalize the concept maps by almost like flattening all the links. So we're going to link all the concept maps together so that you can write graph traversal algorithms to find connections between nodes at very far ends of the network. So imagine this, for those of you who have done comp science, this translates back to the traveling salesman problem, where you have a connected graph, a massive graph with multiple pathways through the connected graph. And so the question to the computer is, given that I'm starting here at this point in the graph on the left-hand side, how do I traverse the graph in the least possible number of hops or steps to the stuff on the right-hand side of the graph? And if you can do that, that is a way to help us answer the question, look, I am here in Colorado. I have this particular situation with a fire that's ongoing now. Give me answers. Find me other graph nodes that have the same similarity to my fire, and tell me what I can do to propose in an emergency response plan to stabilize my slopes, or to stabilize my burn areas, in other words. All right. So this is what we are going to try in the next few weeks. One thing to put out here is there is a monthly conference call that the ESIP Ag and Climate folks, like we put it on every the first Tuesday of every month. Next one is on June the 2nd. Please sign up if you want to join us. For those of you who are familiar with ESIP, you know, these things are, ESIP is an open community, and so you're free to join us. For the ESIP summer meeting coming up in on July, or in mid-July, the Ag and Climate Cluster, we have a specific slot tentatively identified on July 14th. That remains to be confirmed. But if it is ultimately confirmed, we have a slot between 2 p.m. Eastern and 5:30 to go through some of these ideas and to see where we have landed up with this concept map and whether we have been able to make any progress with Neo4j and, you know, modeling the concept maps as a connected graph. So with that, I think I better stop here and take questions. And by the way, what I might do is to just give you a view of these 4 slides, so that if this triggers any questions, we can start off from these slides.
Hi, Brian. This is Leslie. Can you hear me?
Leslie, good to hear from you again.
Hi. Yes. Thanks for this presentation. I've been wanting to learn more about this project for a while, and this was great. And please pardon me, I stepped away for like a little bit in the beginning. So my question, you can just like point me to a slide, but I was looking that top left complicated diagram that you showed, where there were the genomes, which I saw in the small print there. Those are candidate plans, right? Did you talk about how this, just how you came up with that naming? Was it the original community that you were working with, or do you have more detail about that?
Yeah, actually, this. So to tell the truth, when I did my PhD, believe it or not, I spent a lot of time in the lab, dealing with chemicals and extracting DNA. So part of my PhD is actually in landscape molecular genetics, and so I play around with that area. But the genome idea is actually based off also the Human Genome Project. When President Clinton was around, the Human Genome folks, you know, announced a breakthrough in sequencing the entire human genome. And under President Obama, there was actually a materials genome initiative. And so a friend of mine who is now in NASA headquarters, he and I wrote an EOS opinion piece about a year ago, suggesting that we needed a resilience genome initiative, kind of based on the ideas of the Materials Genome Initiative and the Human Genome Project. But the idea is to codify these data to decisions plans in a way that the machine can understand and manipulate. And so when you have a plan that you can use to execute a series of actions, or you can think of that as a genome, because any genome contains instructions for the cell machinery to produce the proteins, for example, including our favorite, you know, the way that the COVID-19 virus hijacks the cell machinery. Anyway, the same idea, right? You have a set of instructions, which is in our case a plan, and in the case of the bacteria and viruses, or even humans, it's encoded in our genomes. But it is a very nice and at least intuitive for some of us to think that we have genome engineers who are tinkering with genomes, for example, to make rice which produces vitamin K, for example, or is it vitamin A? It's one of those two. But when the rice naturally actually does not, when that variety of rice does not produce vitamin A or K, right? I think it's A, by the way, it's vitamin A. So the idea is that to have these cadre of resilience engineers, actually folks like ourselves, frankly speaking, the folks in the room, who have to work with interdisciplinary scientists from a number of different disciplines to put together action plans to help figure out what to do at some level. It could be at the local level, it could be the regional level, probably one of those two levels. Anyway, sorry, that was a long answer to your question about how
No,
that.
yeah, Brian, thank you. It's always very interesting to hear about like the background of how certain words are chosen, and I think that this will resonate with lots of scientists. And even like a little blurb, like it's called genome because it's an actionable plan or something like that, will help people that, you know, like me with a geology background, and then I see genome and I'm like, wait, what are we looking at here? Did I miss something? And I just feel out of my, you know, out of what I know about. So thank you for the explanation.
Oh, you're welcome. But yes, you're right. You're very right. We do need to be careful about the language. I see Jessica Burnett agrees, and I think we have run into this comment many times. I've not actually. I should really do something about it because, in fact, Bill Teng on the phone, he was one of the earlier ones also who critiqued that EOS article about resilience genome, and I believe Bill made some remarks along the same lines about a year and a half or maybe even 2 years ago. But yes, you're very right. I should produce more. I should be more careful about easing folks into this whole genome thing.
Hey, Brian, this is Fran.
Hey, Fran.
I'm thinking that what you're doing here is trying to put together a system that automatically takes somebody's description of their problem and puts together one of these data to decision pipelines using modules that were collected from concept maps that people made out of their own situations. Is that what's going on?
Yes, that's one way. That's an intermediate step of getting. So the concept maps, like here where I'm hovering over, the cursor's hovering over, the concept maps are a way to help the machine cheat a bit, because ultimately what you want to do, and I don't think we can do this in anything less than 15 years. Ultimately, what you want to do is for the machine to go figure things out by turning the machine loose on a bunch of documents. Actually, let it crawl around the web and let it figure out. For any given project, now again, it depends on how you define a project, but for any given project, let the machine figure out this kind of genome, the step-by-step steps that people took. So that is extremely difficult, of course, but which is why I said I don't think we can. I don't think this is possible within the next even 15 years. But so as an intermediate step, we're thinking, to help the machine along, we will cheat by encoding our knowledge in concept maps. Again, now, so there are huge scalability problems, like I mentioned. The creation of the concept maps is not trivial. And if we talk to the community, and community is really pushing that, because we're asking that people document their data by including good metadata. If that already is a high barrier, having them explain their stuff in terms of a concept map, maybe an even higher barrier. But of course, there are ways to get around it if there are relevant incentives. But that's another topic for another long talk, I guess. But did I answer what you were trying to get at, Fran?
Yeah, I think so. I think so, with the added sort of concept that these human created concept maps are ideally something that trains a machine to be able to go through human documents and create and pull out the elements of the genome without the concept map step.
Exactly. And in fact, so I wanted to reinforce your part about, having the human derived concept maps train the machine. That part is critical. In fact, we were in meaning Bill, Riff, and I, we were in discussion with some University of Texas at Austin folks, including a professor who had, asked his students to use concept maps to document their ideas. And so I asked this professor, whose first name is Bill. So I asked Bill along the lines of crowdsourcing. So again, I'm going to take a leap into another domain. Think of Flickr and whale flukes. When folks go on the whale watching trips, right? They take photos of the whales. The flukes are up in the air and they're taking a dive. And so eventually somebody figured out, like, wait a minute, we have all these images that are on Flickr. This is a form of crowdsourcing. We could actually use these images to help whale identification and figure out the migration patterns of the whales. So in the same vein, when we're talking to Bill from UT Austin, I asked Bill, so wait a minute, you've got all these students, drawing out concept maps for some focal, to summarize their thoughts for some focal topic. So can we think about, like, in the same way that Flickr and whale photos are a crowdsourced method to train a machine, can we actually use your students' concept maps to train a machine? If, for example, if for a paper that you get the students to read, if you can associate one or more concept maps with a paper, right? Then it's a really good way to train the machine to associate the concepts that we tend to think about when we read a paper and what the paper is talking about. So if you have that kind of capability, then yeah, this vision of the machine, putting together a plan, or even just helping us to look for documents. So if you, for example, if you look at the Allen Institute for AI, Paul Allen the late Paul Allen of Microsoft, right? His AI Institute funded Semantic Scholar. So and Semantic Scholar is a website that you can go in there and you put in your search terms and it retrieves publications for you. Semantic Scholar does a pretty good job, and the methodology that they use at Semantic Scholar to retrieve papers is actually public. They're very good about making everything they do open. But anyway, back to your statement about having training machines to associate concept maps and ideas. Yeah, that is something that we have talked about just very briefly. We've not really explored that in any depth, but it'll be something interesting to do. Sorry, another long rant.
Thank you. Any other questions? I'm thinking this touches on many parts of CDI, that the relationships is real semantic, but we also have a risk community of practice that is right there in your target application. And then if you start calling things genomes, our eDNA people are all over it, but they may tell you you're misusing the term.
Right.
So it's a cool project that brings together many things.
In fact, your mention of risk and the hazards. It's not division within USGS. I know you guys have the internal structure has changed quite a bit. Wait, isn't there still a hazards?
Yes.
There is, right? Okay. So anyway, yeah, we have one concept actually, which was trying to tie together disparate ways to look at the same thing. So what you have here, this concept map, which is used to tie together climate resilience climate resilience and I don't remember what it. Climate resilience and mitigation, I believe. Well, no, this was a way to tie together climate resilience here and what there is a U.S. approach to managing wildfires. Sorry, I don't exactly remember what it was that this concept map was designed to do, but one of the issues that we had was various frameworks, risk management frameworks and hazard management frameworks, using terms like vulnerability and hazards and exposure slightly differently. And so what this concept map does is we looked at a couple of UN related publications to see how, at least at the global scale, the UN publications, how the UN publications tended to talk about these four essential concepts: risks, vulnerability, exposure, and hazard. And like for the term hazard, we linked it to how the U.S. Climate Resilience Toolkit under President Obama's Climate Action Plan, how the Climate Resilience Toolkit talked about vulnerability versus I don't exactly remember, I cannot remember the trace here, but this is one framework that we attempted to use to unify the different ways that people talk about vulnerability, risks, exposure, and hazards. And so your mention of cross-cutting across USGS and the hazards division reminded me of this concept map. But the idea here, was so that if we have a narrative built on the U.S. Climate Resilience Toolkit, and if the narrative talks about vulnerability, this was a map to allow a machine inferencer to make the connection, to say, yeah, vulnerability was mentioned in the context of the Climate Resilience Toolkit in this manner, but it was also mentioned in this UN publication in this other manner. And so it was a way to allow the machine as a bridging mechanism to find other related concepts and documents which are related to climate resilience, the way that we here in the US tend to look at things.
Thank you. Does anybody else have a question for Brian? Well, this has been very interesting. I think we're going to be talking about this for a little while after we leave. But thank you for giving us this presentation, and I look forward to being able to post the recording and share it with other people in CDI.
Oh, you're welcome. And I need to thank also Megan for jumping in. I think Megan has left. So Megan is our ESIP, one of our ESIP coordinators, who has been very helpful in jumping in to help us out of a little bit of technical difficulties at the beginning of this presentation.
Yes, ESIP is a wonderful resource, but technology is complicated.
Yes. Anyway, friends, thank you for inviting us to give an overview of what we're trying to do.
Yeah, thank you. See you later.
See ya.